Hello everyone. In this chapter, we are going to work on a quick review and introduction to biochemistry. Biochemistry is one branch of chemistry when we are going to work on biomolecules and live systems. For this chapter, we are going to work on basic fundamental concepts of biochemistry, and if you need to have more details, you just need to know we have about 3 biochemistry courses for the students to learn basic, intermediate, and advanced biochemistry concepts. For our class, we just focus on Introduction to Biochemistry. The first group of biochemical compounds that I'm going to talk about them, they are carbohydrates or carbs. When we say carbohydrate, we just need to remember that in our daily life, we use them in different applications. And we don't call them carbohydrate or carbs, we call them sugars. So in general speaking, carbohydrates means sugar in the chemistry. And when we talk about one of the most important compounds in our diet. When we say sugars, I'm sure you remember this formula, for example, C12H22O11, or you may remember C6H12O6. So there are some examples of sugars or in general carbohydrates. I'm going to talk about the meaning of carbohydrates in this section. When we say carbohydrate, so you may easily understand we have carbon in the compounds, and when we say hydrate means H2O. So when we say carbohydrate, it means we have a compound composed of carbon, hydrogen, oxygen, and always we have this relationship between hydrogen and oxygen. 2 hydrogens, 1 oxygen. So this ratio should be repeated here. So general formula for the carbohydrate is CH2O, and we are going to repeat that one by several examples. If n is going, for example, 3, if we have n 3, we may say CH2O will be repeated 3 times. So we are going to have C3H6O3. As you see here, we have 3 and 6. The ratio is 1 and 2 for H and oxygen, so like H2. If we have, for example, N6, we call that CH2O will be repeated 6 times. So we have C6H12O6. So this is one of the carbohydrates. We know that the relationship between oxygen and hydrogen is 1 to 2. But as you see here, for some carbohydrates, we have something different. We have 2 and 1 relationship between oxygen and hydrogen, but the number of carbon is not same as number of oxygen. Look, in this example, in this formula, the number of carbon and hydrogen, carbon and oxygen must be same. We are going to know what happens and how we can explain these changes. One thing before talking about the carbohydrates and working on the different types of the carbohydrate, I'm going to remind you, in biochemistry, we may use different methods to call our biochemical compounds. Sugars in biochemistry has one rule to call. So if we have a compound ends to O's, OSEOs, we call that sugar or carbohydrate. For example, when we say glucose, when we say fructose, so you may call some more. If you remember that one from the other courses or in general information you may have. So if something ends to O's, we call that sugar. So our sugars, they have this suffix at the end. Glucose, fructose, they are some daily used sugars in our life. Another method to represent carbohydrate or call carbohydrate based on the number of carbon atoms in the sugar or carbohydrates. If we have, for example, C3H6O3 like this one, the number of carbon is 3. So we call that triose. It means we have 3 carbon atoms in this sugar. If I have like this, tetraose, if you remember that when we have 2 vowels, we drop the first one, so we call that tetrose. In this sugar, we have 4 carbon atoms. So I may say we have C4H8O4 because we want to work on this CH2O 4 times. So it gives us C4H8O4. Another example, pentose, 5 carbon atom. Hexose, 6 carbon atom. So this one of the example of hexoses. It means 6 carbon atoms in the formula. So one of the classification for the carbohydrate is based on the number of carbon atoms, tetroses, pentoses, hexoses. In general, hexoses are most commonly used sugars for human for our daily life. So we use mostly hexoses as a sugar in our diet. So I will back and talk about C12H22O11 and we are going to know what does happen over there. Another classification for carbohydrate is classification based on the potent or parent formula. We may have different classification based on the history of the carbohydrate. With advanced classification, we say carbohydrate can be classified as 3 different groups: monosaccharide, disaccharide, and polysaccharide. Mono means 1, di means 2, and poly means when we have more than 2. In general, poly means many. So whenever we have more than 2 components, we call that di. We are going to know what does that mean when I say components or parent formula for the sugars. So please memorize that carbohydrates can be classified as mono, di, poly. Monosaccharide, disaccharides, and polysaccharides. We are going to know what is the meaning of one or monosaccharides. As you see here, it says the simplest carbohydrates. So the first class of the carbohydrates. They have in general carbon atoms and OH groups. We are going to know what does that mean. It says monosaccharides have carbon atoms and OHs. Let me show you in this slide some examples of monosaccharides. So please review that one again. They have carbon atoms in a chain with carbonyl group and many OHs. So I'm going to explain for you what is the meaning of these keywords here. They have carbon atoms. So we are going to work on organic compounds or biochemicals. It means we definitely have carbon atoms because in organic chemistry we do have carbon atoms as essential elements in the compounds. In a chain, so if I write many carbon atoms, several carbon atoms like this or like this, so let me draw like that one to make sure no confusion. Look here, several carbon atoms are placed in a line, in a chain. So we call that one linear compound, or we call that we have a chain. We have a chain. A series of the elements can be repeated, like the carbon in this series. Then it says many OH groups. Please look here. So for each example, you see as a carbohydrate, OH repeated several times, as you see here. So we are going to review that one. We have a formula with carbon atoms are placed in a chain with many OH groups. As you see here, one part of each compound, I didn't draw anything. And I'm going to draw a box here. You see CHO, here, CHO here, and for this one you see C double bond O, Back to this one. It says with a carbonyl group. Guys, in chemistry, we call C double bond O, when you see C double bond O, we call that carbonyl group. C double bond O. So it says they have carbon atoms, OH groups, and a carbonyl group. Please look here. In this one, we have carbonyl groups. But where is the carbonyl group or C double bond O here? CHO has this chemical structure. C, let me draw like this one, double bond O, and here we have H. CHO. So it looks, whenever we write CHO, we do have C double bond O, and we call that carbonyl group. So I explained for you the different parts of this definition. Monosaccharides are simplest carbohydrates. They have in general carbon atoms in a chain with many OH groups and a carbonyl group. Right now, I'm going to work on a difference between the carbohydrate you saw here. Here we have only C double bond O. Here we have C double bond OH. We call that CHO. In chemistry, C double bond OH, like this, we call that aldehyde. And C double bond O without hydrogen, no hydrogen, we call that ketone. We call them in general functional groups. What does that mean, functional groups? Functional groups means when we are going to look at the formula, if I look at the formula and find we have C double bond OH, I can predict some behaviors or properties of the compounds by looking at the chemical formula. If in the chemical formula I have C double bond OH, we call that aldehyde. So I may say this compound belongs to aldehyde group and it has some properties like this. If we have C double bond O, we call that ketone. So the sugars, we work on them. Aldehydes appear in the sugar only on carbon number 1. And ketone appears on the sugar on carbon number 2. So there is difference between aldehyde and ketone when we are going to put them in the sugars. Please look, carbon number 1. If we are going to count the number of carbon, 1, 2, 3. So first carbon atom we have CHO. 1, 2, 3. The first carbon atom we have CHO. Here 1, 2. On second carbon atom we have carbonyl or ketone. So always ketone are placed on the second carbon atom, and aldehyde are placed on the first carbon atom. Right now, I'm going to work on this definition. Monosaccharides with a carbonyl at the C1, we know them, we call that aldehyde. We call them aldoses. It means sugars have aldehyde, we call them aldose. Aldose means we have aldehyde in the formula, in the sugar. If we have ketone in the formula, ketone is placed on the carbon number 2. We call that ketose. So whenever you see ketose, it means we have ketone functional group. It means we have like this in the compound. It is going to place on carbon number 2. So let me erase this slide. Right now, I'm going to classify these examples. We have these 3 sugars here, and I'm going to know which one is aldose, which one is ketose. I look at the formula, aldose, aldehyde CHO, we call that aldehyde. So it's placed on the first carbon atom, we call that this compound is aldose. For the second one, we have CHO at the first carbon atom, so we call that, we do have aldehyde. So this is another aldose. This is another aldose sugar. How about this one? Fructose has C double bond O on the second carbon atom. So we have ketone. So our compound, our sugar is ketose. Right now, I may say something regarding these examples. This sugar and this sugar belongs to aldoses, and they have some similar properties. This sugar belongs to ketoses, and it has different properties with aldoses. So this is the classification we need to know for aldoses and ketoses. So I am going to back to this slide and hope you got that one, what we need to know for the monosaccharides. So monosaccharides, again, we have a chain of carbon atoms and OH with carbonyl group. Carbonyl groups means we may have aldehyde or ketones. Aldehyde make aldoses and ketone makes ketoses. How to identify, how to distinguish aldehyde and ketone, aldoses and ketoses. In biochemistry, we have one test. We call that test Benedict test. Benedict is the name of one scientist who worked on this concept, and he proposed a reagent. We call that Benedict's reagent, and his test, we call that Benedict's test. This is the basic and most commonly used test to identify what type of sugars or what type of carbohydrate we have, if we have aldoses or ketoses. By this test, we are going to work on this differentiate. Benedict test is going to identify we have aldose or ketose. Aldoses or ketoses. Benedict reagent composed of some solution of copper 2 positive. Copper 2 positive. So example for the reagent is CuSO4. Copper 2 sulfate. If you would like to know what is the formula of this reagent, so the main component of this reagent, this is a solution. So it means we have something else besides of it. It's CuSO4. Benedict test is blue, so easy to memorize. Benedict test is blue. When we add Benedict test to our sugars, only aldoses have positive test, positive response to our test, and ketoses have negative. There is no change for ketoses. How to find we have positive test for aldoses? If you add the blue reagent to your sugar and if you see red color, blue convert to red, we say we have positive test. It means we have aldose. If there is no change, we still have blue. No change, nothing happened here. It means we have ketose. So ketoses have negative test and aldoses have positive. So this is one thing. You just need to add a couple drops of Benedict's reagent to your aldoses to get the color change. If we have color change, we call that positive aldose. Otherwise, we call that ketose. In chemistry, this change is going to happen for aldehyde. So we are going to convert aldehyde to this formula. COOH. Look here, when we have COOH, we call that carboxylic acid. So in chemistry, if we have C double bond OH, we call that carboxylic acid. So let me review for you the functional group we studied so far. If we have C double bond OH, we call that aldehyde. If we have C double bond O, we call that ketone. And if we have C double bond OH, we call that carboxylic acid. When you add Benedict's reagent to your aldoses, you are going to change this one to that one. So aldehyde convert to acid. We call that these sugars, aldoses, we call them reducing sugar. So one term we may use for aldoses, reducing sugar. And when we have ketones, they don't have any changes. We call them non-reducing sugar. There is no change for them. So they are different classification. That is why I said you just need to take 3 courses biochemistry if you are going to learn that one. Today we are going to work on an introduction. So please remember that we have 2 types of sugar, aldoses, ketoses. How to distinguish what type of sugars we have? We just need to work on Benedict test. Add a couple drops of your reagent. If we have color change, we call that we have aldose. If there is no change, we call that ketose. Color change means from blue to red. Aldoses, they have change. We call them reducing sugars. And when there is no change, negative, we call them non-reducing sugar. So they are something you should know as this part of our class. If you remember, we talk about 3 different types of sugars: monosaccharide, disaccharide, and polysaccharide. We talk about the monosaccharide. So disaccharides are carbohydrates composed of 2 monosaccharides. So this number 2, it means 2 monosaccharides. For example, if I have C6H12O6, so look at this formula, CH2O is going to be repeated 6 times. C6H12O6. So it means we have monosaccharide. If I add this monosaccharide to another monosaccharide, C6H12O6, the formula makes disaccharides. But we just need to know that whenever we are going to combine or join these 2 monosaccharides, we are going to work on like this formula, they are connected with one oxygen atom. So the bridge between these two monosaccharides is only one oxygen atom. If I'm going to write the formula for that, if you add this C12H24O12, as you see here, if you add these two, you may see like this. But always, whenever we are going to make a monosaccharide, we make H2O. So you need to remove one H2O from this molecule. So remove one H2O from this molecule. Let me write the formula. C12H22O11. So this is the formula of disaccharide after connection between these two monosaccharides. So this type that it doesn't follow the formula, so we call that disaccharide, or we call that one, it composed of two monosaccharides. Always, whenever we are going to connect two monosaccharides, you just need to add the formula and remove one H2O, because H2O is going to be produced as a one product in this reaction. We call that dehydration. We are going to remove H2O. So this is the formula of this one. And since I made glucose for this example, glucose, the disaccharide called maltose. If we have glucose and fructose, we have another sugar. So we have a variety of disaccharides. So you may combine any monosaccharides with each other to make the disaccharides. Whenever we are going to work on formula for disaccharides and polysaccharides, we prefer to report the sugars in like this form. We call that cyclic form. Cyclic means we have a ring in the formula, like this one. So we are going to represent and show the chemical formula of sugars, carbohydrates by two forms. Cyclic, when you see a ring, or when we have a chain. So two forms to report the carbohydrates. When we have chain, when we have ring. So hope you learned that one regarding monosaccharide, disaccharide. Right now, we are going to work on lipids. We are going to work on another type of carbohydrates. We are going to see what does that mean when we say lipids. I'm sure you are familiar with this definition. Lipids are biomolecules that they cannot dissolve in water. So water is a polar molecule, and in chemistry we have one thumb rule. We say like dissolves like. When we say like dissolves like, means polar dissolves polar, non-polar dissolves non-polar. What does that mean, polar or non-polar? Polar means, for example, in the Lewis structure, if you remember that, we have lone pair for the central atom. We have different groups of electrons around the central atom. When we say polar and non-polar, we can explain some properties of the compounds. When we say lipids are insoluble in water, it means they are not polar. So it means lipids are non-polar compounds. They are non-polar compounds, and we cannot dissolve lipids in water. In other words, if you add lipids to water, Assume that this is a water. So here, for example, we have lipids. Lipids cannot dissolve in water. So you will see a combination of two different compounds, a mixture of two different compounds. We call them mixture. And we call that heterogeneous mixture because you cannot combine or mix through these two compounds. You see both components. Both components are visible for us. So lipids are insoluble in water nonpolar compounds. We are going to know why do we have nonpolar compounds for lipids. The formula for lipids is composed of carbon, carbon single bond, carbon, hydrogen, and COOH. We already talked about this in our class in the first section in this video. COOH. Do you remember what did we call that? I'm sure you are going to say carboxylic acid. So it looks lipids, they have carbon, hydrogen, and carboxylic acid in the formula. One of the information we need to know for the lipids regarding their building blocks. Their building blocks is fatty acids. Why do we call that fatty acids? Because we have COOH, carboxylic acid in the formula. And fatty acids, they are defined as compounds composed of carboxylic acid with this number of carbon atoms between 12 and 20. So if I'm going to give it you one example of the fatty acids is this example. If I look at the formula, I say I have acid. The number of carbon atoms, look here, C, C, and C. I'm going to count this. One carbon atom here, carbon atom in the parentheses and 14. So it looks we have 14 carbon atoms here and one carbon atom for sugar. So totally we have 16 carbon atoms. So if we have in biochemistry, we say that if we have a compound, it has carboxylic acid and has between 20 to 20, we call that fatty acids. So this is one example of fatty acids. In chemistry, we use the ball and stick model. Ball and stick model. Carbon atoms always we use by, we denote them by black ball, and this stick it represents covalent bond, and the gray or white ball it represents hydrogens here. How about this one? What do you think about that? Look, carbon black one, double bond, O. So red color represent oxygen. So it means we have C double bond O and H. O and H. So this is a model we use in our chemistry labs to report and show the molecular form, molecular shape or geometry of large molecules like fatty acids. For our class, you just need to know this classification for fatty acids. In general, we have two types of fatty acids, saturated fatty acids and unsaturated fatty acids. It's easy to follow and learn that one. Saturated, unsaturated. Saturated means no double bond, no carbon-carbon double bond in the formula, but for unsaturated, we do have carbon-carbon double bonds, at least one. So if I look at the formula, and see carbon-carbon double bond, I call that this is unsaturated fatty acid. If I look at the fatty acid formula, there is no double bond, for carbon-carbon, I call that saturated. So let's see what happened in this example. In this formula, I see everything is going to repeat it here. So here only COOH. Look, COOH. There is no carbon-carbon double bond. There is no carbon-carbon double bond. So we call that saturated fatty acid. So this one is one of the example of saturated fatty acid. How about this one? Please look in the formula. In this side, I have carbon-carbon double bond. As you see here, we have carbon-carbon double bond. 1, 2. We have a double bond. So in this formula of fatty acids, we have carbon-carbon double bond here. So we call that unsaturated fatty acids. This example. Now back to this slide. Oils are example of unsaturated fatty acids. In our daily life, you have two types of fatty acids, solid and liquid. Oil is liquid one. I'm sure you may say oil is the liquid fatty acid. Oils are example of unsaturated. In general, unsaturated fatty acids like oil, they are liquid. So unsaturated fatty acids like oil, they are liquid fatty acids. Solids, they are saturated one. So if we are going to know what type of fatty acids do we have in general, fatty acids in solid form, we have saturated one, and if we have liquid, it means we have unsaturated. Butter is one example of saturated fatty acid. Guys, I said in general. It means we do have some examples of unsaturated solid or saturated liquid. But in general, in the first step of production of fatty acids, we have like this one. And last thing to remind you, whenever we say, for example, omega-3, I'm sure you heard about omega-3. Omega-3 is one of the fatty acids. What does that mean, these three? These three represent the position or place of carbon-carbon double bond. The place or position of the first carbon-carbon double bond. Look at this formula. Look at this formula. In this formula, we have carbon, hydrogen, and COOH. So this is a fatty acid. If I count the number of carbon atoms, it should be a number between 12 and 20. On carbon number 3, carbon number 1, 2, 3, we have this double bond. The first double bond carbon atoms are placed in carbon number 3. So we call that omega-3. How about if we say omega-6? How about if we say omega-6? So you have a compound, carbon-carbon double bond are placed on carbon number 6. So we call that omega-6. Right now, please let me know, what do you call that one, if in case we are going to call by a number. You just need to count number of carbon atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9. So, for example, if we are going to call that, we may call that omega-9. So, this is a place of first carbon double. Alright guys, right now let me work on another group of biomolecules, amino acids, proteins, and enzymes. We are going to know how they are going to relate it to each other. Again, each of these three, they have a lot of information and we need to work by the details in real biochemistry courses. In general, proteins are biomolecules contains many amide bonds formed by joining amino acids. We are going to know what is the meaning of amino acids when we are going to combine or join amino acids. Look at this formula. We have carbon. Carbon group number 4, 4 valence electrons. 1, 2, 3, 4. It means we need to have 4 bonds for carbon atoms. We say amino acids. Acids in the organic chemistry means COOH. Do you remember that? We call that carboxylic acid. So one side we have COOH. On the other side, we have one compound, we call that amine. This is a group. Amine has like this one, NH2 group. So I write like this, NH2 here. So this part is amine, this part is acid. So if we have a carbon atom, one side has amine, one side acid, we call that amino acid. Amino acids, they have 2 more sides. Always for one side we have hydrogen. Always for one side we have hydrogen. And in other side we have R, or group of carbon atoms. So R can be varied, different group of carbon atoms. So you may put that one CH3. Let me write it here. R can be CH3. So you may put this here CH3. R can be C2H5. So you may have C2H5. So we have different types of amino acids based on this R, because R is changed. So in formula, this structure, amino acid, has amine, acid, hydrogen. It would be same for all amino acids we have in chemistry, and R is going to be changed. If we can join amino acids to each other, we are going to work with a new group of compounds. We call them proteins. Let me talk about the proteins by more accurate definition in next couple of slides. As you see here, when we are going to connect the amino acids, we are going to connect like this. Look, here we have N, it means amine, and C double bond O, it means we had OH. Whenever we combine or join amino acids, H2O can be removed. H2O can be removed. I'm going to remove H2O here. H2O, H and O from this part, H2O. So I removed H and O from this, and one hydrogen from that one. So whenever we have amino acids in the structure, we have HN and CO. Look here, COHN, 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 and it's going to be repeated because we remove H2O when we join amino acids. So if we have only one amino acid, we have like this. If amino acids join each other, they are going to remove H2O, and this removing H2O makes CO on one side and NH on another side. This bond between each amino acid that you see by the red color in this slide, we call them amide bonds. Amide bonds means bridge or connection between two amino acids. We are going to talk about proteins. You just need to know that when we say proteins, we are talking about different types of proteins. We have many types of proteins in our body, and for each one we have some functions. So one of the most important studies in the sciences, specifically in chemistry and biochemistry, is a structure function study. Based on the structure of your compound, you can predict the function of the compound. for proteins, when we study proteins by their structure, we can predict some functions of them. Since we have many proteins, we have different functions in our human body. As you see here, for your example, you are not asked about this on your exam. Only for your example, we have this type of proteins in our body. They are in general essential proteins for humans. So I already talked about amino acids, general features of amino acids. Amino acids contain amine on the left side, acids on the right side. It doesn't matter left or right, it doesn't matter at all, but we prefer because we call that amino acids. We start with amine on the left, acid on the right, and hydrogen on the top, and R is going to be repeated. This carbon, we call that by one specific term, we call that alpha carbon. So when we are going to study by details, when we are going to talk about the carbon atoms, because we have, for example, these two carbon atoms in generic formula, we call this carbon atom alpha carbon. It's not necessary to know that. So I already talked about that one. I'm sure that you are able to answer some questions regarding the structure of amino acids. We are going to continue to talk about some features of amino acids. Guys, only 20 amino acids can be available naturally, can be synthesized naturally, can be produced naturally. Only 20. Our body can make only 10 out of these 20. Only 10 of these 20. So how about for the rest? I'm sure you have the answer for this one. As you know that the remaining 10, we need to get that one by our diet, by supplements. So next 10, we just need to get that one based on our daily diet. In our lifestyle, we need to consider, we need to have 10 essential amino acids. So that is why it's very important you have a very regular diet to get these amino acids for your daily life. I talk about amino acids. I wanted to talk about proteins, but I'm going to talk about another ones, peptides. We are going to know what does that peptides. We said proteins are formed when we join amino acids by amide bonds. We already talked about this one. We already talked about this. And I explained for you what happens if you add two amino acids to each other. Dipeptide, it means we have two amino acids. Peptide is the name of this bond, amide bond. So let me write one amino acid here, COOH, R. This is the first amino acid. I'm going to add to another amino acid. I told you, whenever we are going to add these two, we need to remove H2O. You need to remove H2O. Always, whenever you are going to remove H2O, OH from acid side and H from other side. So I'm going to write this formula here. H2NCHR. Here we are going to have CO, make a bond, NH. And let me write H like this, CH, R2, COOH. So this is the compound if we add these two amino acids. This bond, it connects, it makes a bridge between the first amino acid and the second amino acid, like this. Let me draw better. We call that peptide bond. Peptide bond. This. Since I connected two amino acids, we call that dipeptide. If I add three amino acids to each other, we call that tripeptide. If we make four amino acids join each other, the formula make tetrapeptide. How about if I join 5 amino acids? We call that pentapeptide. And we are going to continue like this to find proteins. Please pay attention. The formula I wrote here and here is slightly different because I remove H from this one and I added this here. So for this, whenever we add amino acids to water to make a solution, so to make a solution we need to have polar compounds. Polar compounds because water is polar. Polar means pole, positive pole, negative pole. So we remove hydrogen to make positive pole here, negative pole here. So it helps us to dissolve. Water can dissolve something like peptides. We don't work with this. You just need to know what is the meaning of dipeptide, tripeptide, pentapeptide, and so on. Right now, I'm going to talk about proteins. Guys, proteins. Polypeptide, it means many. We call them proteins if we have 40 amino acids, more than 40 amino acids. So, dipeptide, tripeptide, penta, tetra, hexa, hepta, octa, nona, polypeptide. If we can connect 40 amino acids, we call that proteins. Proteins. So let me write this here because we should respect to the proteins. 40 amino acids. Please memorize that. If we add 40 amino acids, we make proteins. If you remember, I talked about structure function. If you look at the formula, if you look at the structure, you can predict the formula. In general, we can report the proteins by some form or some versions of structure. First one is primary structure. We draw amino acid like this, and we see like this arrangement up and down. So we call that one primary structure. Primary structure. Primary, we write like this. Secondary structure. Secondary structure, if we have our 3D arrangements in the protein like these two forms, alpha and beta. Alpha helix and beta, we are going to see what does that mean. So for primary, we have like the basic form that we use in the chemistry classes. For secondary structure, we have two types, alpha and beta. Alpha helix, whenever we see something like this, like curl. So whenever we have something like this, as you see here, we call that alpha. Beta, whenever we have like a parallel plane. So this form it represents beta, this form it represents alpha. So please learn that one. Alpha whenever we have like this form, beta whenever we have like this form. So this is like a plate. And whenever we are going to study functional protein, we just need to know what structure of protein reported for our protein. In general, when we have like this and we cannot determine we have alpha or beta, we use this random. It means we may have alpha, beta for our proteins. We could not detect or determine exactly here. Look here, this is a formula of proteins. More than 40 amino acids. They are linked, connected, join each other, and we have like this. If we are going to report this ball and stick model in the shortest or easiest way to follow, we may report that one. Here, this is alpha helix, alpha, and this part by the purple color, we have the beta, and for this part, we don't have any definition for this one because they are not going to be repeated like alphabet. We call this random form. This is one of the example of alpha helix as you see here. This is only for fun. Please understand this is for fun. When we talk about enzymes, we are talking about one type of proteins. One type of proteins that they serve as a catalyst in our living systems. Catalyst, it means they speed up the reaction. They increase rate of reactions. So we use enzymes to make our reaction in the short time. They are going to be completed in the short time. Proteins, if they act as a catalyst, we call them enzymes. So enzymes are proteins and they have some specific functions. That is why for each concept, each study, each function, we need to work with a specific type of proteins. For example, if you are going to work on lipids, the proteins that connect with the lipids, if it's used as an enzyme, we call that lipids. So ASE represent our enzyme. So it means it's used for lipids, hydrolyze. This is enzyme. This is a protein. It means it's used to hydrolyzes. Hydrolyzes. So proteins can be used to speed up our reaction, to increase rate of reaction. So we call them enzymes. So please remember that enzymes are one type of proteins that act like a catalyst, a speed up of reaction. And the last two groups of compounds we need to work on whenever we talk about nucleosides and nucleotides, we are going to know what is the difference between them and what are the similarity between them. First, building blocks of nucleosides, we call them nucleic acids. Nucleic acids are polymers. It means they are repeated 100 times, 1,000 times, many times from the nucleotide. Nucleotides are building block of nucleic acids. So for nucleic acid, we have two types, DNA, RNA. I don't want to talk about this because I'm sure you know that. DNA stands on desoxyribonucleic acid, and RNA, we are going to work on ribonucleic acid. So DNA just have this function, it stores the generic information, and RNA translate this information. So DNA are most important part of this section because they can keep the genetic information. Whenever we say our nucleotide, we are talking about these compounds in the nucleotide. Nucleotide has monosaccharide, N-containing base. We are going to know what does that mean, and phosphate group. We already talked about monosaccharide. Monosaccharide means carbohydrate. You may report as a cyclic or as a chain. So this is a monosaccharide. Phosphate, PO4, 3 negative. PO4, and we have 3 negative here. So 3 negative, here we have the negative here, it's combined with positive, and that is why it's neutral, right? So PO4, 3 negative here. And one side N-containing base. In chemistry, in organic chemistry, if we have a compound with nitrogen, we call that base. For example, if we have NH3, we call that base. Please remember Brown-Stott-Lowry base. So for amino acids, if you remember that, amino acid, this is acid, amine, this is a base. So in general, amino acids, they have base and acid in the formula. That is why they can make most important compounds in living in the very life system. Whenever we are going to live, we need to have this information of compounds. They are acting sometimes like a base, sometimes like acid, and they are going to make proteins. So that is why it's important for us, for our daily life, to have amino acids, because they are going to balance acidic part and basic part of our body. They are going to make the proteins in our body. So back to this one. If you have a compound with the nitrogen, we call that base. So it says N-containing base, it means we have a base contains of nitrogen. Whenever we are going to find what is the difference between DNA and RNA, we may say DNA composed of million nucleotides, but RNA, they have only few thousand of nucleotides. So nucleotides means this structure. Million of these make DNA, few thousand make RNA. Whenever we are going to talk about another differences between DNA and RNA, it goes back to their monosaccharide. Ribose is this sugar. For RNA, we have ribose, and whenever we have DNA, we have desoxy. Desoxyribose, it means we don't have OH on the ribose. So OH means hydroxyl in chemistry. Hydrogen, oxygen, OH. When we say desoxy, it means dihydroxyl. So we drop that one. We call it dihydroxyl or desoxy. Desoxy, it means we don't have OH. We don't have OH here. So this is the desoxy, this is the ribose, desoxyribose and ribose. So we don't have the monosaccharide for RNA, same as DNA. For RNA, we have ribose, and for DNA, we have desoxyribose. So this is another differences between them. Also, another differences between the DNA and RNA is based on their base. So in the formula here, we talk about the DNA and RNA difference between these. PO4 always is same, but the number of bases can be placed here is different. We have different types of bases, so we may have different formula. For bases with the nitrogen, look, these bases, they have nitrogen. So we have different types of bases here. So we use like this notation to represent each one. One thing we should know, so we are still continuing to report them. One thing we should know, for DNA, we can accept only these 4 bases. A, G, C, T, and for RNA, we can accept only A, G, C, U. So it looks there is difference between RNA and DNA in one of the bases. DNA can accept only T and RNA can accept only U. AGC is commonly used bases between these 2 nucleotides, DNA and RNA. Guys, I'm going to review that one, DNA and RNA. So please understand, we are going to work on the structural formula. This is one example of nucleotides. PO4 phosphate added to monosaccharide added to one of the bases. So this one, we are going to make our RNA because here we have the sugar, we call it ribose. Why do we need to know this information? Because in DNA, if for example we have like this strand is alpha helix, for example here, always bases can be paired like this. A, C, G, T. Always C and G can pair with each other and A and T with each other. AT, CG. They are going to make a bond and it helps the protein structure be strong and work with our body system. So, for example, this is the G, this is the C, the formula between 2 different sugars, and we may have the attraction or bond between them. This attraction in chemistry, we call that hydrogen bond. Hydrogen bond. Always between GC and TA, we have hydrogen bond. So the reason we can keep these 2 because of hydrogen bond. For our class, you just need to know always AT and GC can be paired with each other. So right now, I'm going to work on some examples. We are going to write a template, a strand, and see how to write the complementary form for this one. For example, we have like this one, AA, TGC, TAC, TGAC. Assume that we have this portion of a strand, and I'm going to work on complementary part of this. So always I have to pair A with T and G with C. Assume that we have like this one. T, T, A, C, G, A, T, G, A, C, T, G. So always you are going to pair like this one. So for this example, I may ask you to pause the video and answer this one. How to write the complementary base sequence for this instrument. Right now, please compare your answer and see is there any typo or not. Alright guys, as you see here, we can write the complementary sequence for basic part of DNA like this one. Please memorize like this. CG and AT can be paired by each other. Alright guys, this is the short review and brief explanation regarding the introduction of biochemistry. Thank you for watching and hope it would be helpful for you guys.